Okay.
Well, what gets me is part of this big question on his exam. It was mentioned in his notes. Oh, this is in a sub-document in another folder. Go take a look at it.
Okay, folks, we're ready to get started again. I want to talk some about the physical constraints of solar energy. Of course, everybody understands that we live on a sphere, right? It's relatively spherical, and the sun is someplace far away, and it sends slight rays toward the Earth, and by the time the light gets here, all the rays are relatively parallel to one another. They're going in the same direction. And of course, we're not at the equator here. We're about plus 43 degrees up on this sphere. And so what that means is that for much of the year, the sun has to penetrate a deeper part of the atmosphere. As you go into the atmosphere at an angle, you have a deeper atmosphere to penetrate before you get to the conversion technology, which in our case would be some silicon photocell technology. So the result of the sun having to travel through a deeper segment of the atmosphere means that more energy gets scattered out. There's a thing called Rayleigh scattering and Mie scattering, which takes this radiant energy and tends to make them move off in a different direction. And in fact, that's why the sky looks blue, is because the longer wavelength energy is being scattered out by the atmosphere, and only the shorter wavelengths are able to color it. The fact is that solar cells have their maximum quantum efficiency at around 8 to 900 nanometers wavelength, which is infrared. It's the near infrared spectrum. And that's one of the wavelengths that gets scattered by the atmosphere. So the more atmosphere you have to go through, the less energy available to the cells. On much of the Earth, closer to the equator, you get about 1 kilowatt per square meter from the sun. And that's the total amount of energy that the sun is putting on the planet. The solar panels themselves, though, have much lower efficiency. And so depending on how much money you're willing to spend, you might get efficiencies from 18 to 25%. So of that kilowatt per square meter, you might get 250 watts at best, and it's usually less than that. It's on the order of less than 200 watts per square meter usually is what you're able to collect when you have a clear view of the sun. The other thing about solar panels is that the voltage that they generate, which is a function, the voltage is important because power, as hopefully all of you know, is voltage times the current, right? And so the voltage on the solar cells is important. And as it turns out, the band gap voltage on silicon cells, they have a p-n junction in there. The band gap voltage actually declines with temperature. And so as the panels themselves get warmer, their capacity to generate energy goes down. So it's always helpful if you could keep the panels cooler, or at least give them proper ventilation so that they don't get any hotter than they have to be, because that'll reduce the power output by virtue of the voltage being decreased. Solar panels are a quantum conversion device. That means that when a certain amount of radiant energy excites this p-n junction, it releases an electron-hole pair, which is what generates the current. Okay? So unlike a battery, if you take a battery, say a car battery, and you were to take a piece of wire and short circuit across the two car battery terminals, what would it do? Anybody had that experience yet? No, come on, you tell us how much. It might explode, actually. Car batteries have very low internal resistance, and so if you were to put a wire across the two terminals, the current flow could be on the order of 400 or 500 amps. Okay, with that much current, it would generally fuse or melt the conductor. It would just explode and a bunch of metal flying around. It might not be very pleasant. So don't try that experiment at home. But the fact is that solar cells are much different in this, in that they don't have an internal impedance. What they have is an internal quantum efficiency. And so solar panels are intrinsically current limited by their capacity to convert radiant energy to electrical energy, right? And so if you have a panel that's designed to produce 10 amps, because of the size of the panel and its exposure to light, they tell you in specification that it's going to be a 10 amp panel. What that means is, even if you were to take the wires from that solar panel and short them directly together, you're not going to see significantly more than 10 amps. In fact, it might even be less. the efficiency of the panel will vary based on the load impedance. And so you're limited, in fact, the current that could pass through those wires based on the quantum efficiency of the panel itself. So you're not going to have like hundreds of amps and blow things up. And so it's not uncommon in solar panel designs that you might not even put a fuse to protect the solar panel, because even if you had a short circuit on an individual panel, the amount of current available to do damage is not very much. And most switches and conductors can tolerate a 10 amp current without much problem. The next thing is the way the panel itself converts the energy. You know, the energy has to penetrate into the silicon material to a certain depth in order for it to be absorbed and have this phenomenon of generating holes and electron pairs. And if the light hits the panel at a glancing angle, it's less likely to penetrate to the depth that's going to be useful for generating the electrons that you need for current flow. And so you'd like to be able to keep the panel normal to the light rays, which means perpendicular, right? You'd like to be able to keep the panel perpendicular to the light rays all the time. Well, unfortunately, because our planet is turning on its axis, you don't get to do that. And if you have a stationary panel, the sun moves from one angle overhead and then onto the other side. They do make solar systems where they have computers and servo mechanisms that will keep the panel pointed directly at the sun all the time, which can increase dramatically the efficiency, especially in northern climates. And so depending on the budget you have to design your solar power system, you might think about designing one that has technology to keep it pointed directly at the sun.
What's your personal opinion on trackers?
I've seen them installed in a number of places. Like I said, again, it depends on the location. For example, in Kenya, when I put the systems there, that was directly on the equator. And so we actually had a very long exposure of high incidence angle to the panel. And so it would not have been too practical to use it there. But say here in Toronto area, the amount of sunlight that comes in a winter day is much shorter, and at this glancing angle through the atmosphere, so it has a much deeper atmosphere to go through. So to improve the efficiency, you might see significant gains, I mean really significant gains, by being able to track the sun through the sky as it goes. I've even seen some trackers, you know, when you have a cloudy day, you can't see the sun sometimes. It's just obscured by clouds, but it may not be raining. But I've seen some trackers that have internal clocks. And so rather than using a photocell detector to find out where the sun is, they have an internal clock that calculates where the sun must be. And it'll point the panel at the sun even if there are clouds obscuring it. And that helps also. So that's a little bit about how the energy gets into the panel. Again, like I mentioned, you'd like to keep the panels cooler because we get the higher band gap voltage, which increases the efficiency of the solar panel's output. Now, when you start collecting energy on solar panels, you're dependent on the sun. And so there are a lot of reasons why you may not have very much sunlight available. Throughout the seasons, you know, the sun changes elevation above the horizon. The sun moves to the Tropic of Capricorn and the Tropic of Cancer back and forth, which are each 23 degrees above and below the equator. As the sun moves to the lower extreme, the sun is closer to the southern horizon at noon. And as it moves to the higher extreme, the sun is higher. And so you get that change in angle over the course of months, you know, where it goes from this angle to that angle. And also similarly, I mentioned before about during the daytime, it goes from one end to the other every day from east to west. So you have this excursion. Now actually in the northern climates, the angular difference for the sun between winter and summer is not as great as it is in the southern climates. And so you can tilt your solar panel to the south, and in terms of the azimuth, it's not going to, or the elevation I should say, the elevation is not going to change that much. Since we're 43 degrees north latitude, you want to have your panel up at about what angle would that be? Between the ground and your panel, since we're 43 degrees north latitude. How about 57? So it's a complement of 90 degrees. Right? So you want to have a 57-degree angle that holds your panel up, and then in that position, over the course of the year, you'll average the best angular displacement in elevation. Okay. And the other thing you want to do is face it directly south, so that as the sun moves across from east to west, you'll get the best exposure. Does that make sense? Does everybody understand how that one works? Now, the next thing about the illumination of the panels is that, we're going to go through the process once we examine the farm of developing an energy budget. Basically, we're going to figure out exactly how much energy is required at any given time, day or night. For example, if energy is required when the sun's not available, we'll have to have some storage mechanism, a battery of some kind. And so what our energy budget is going to tell us is that we have to collect enough energy so that we can be charging the batteries to be able to provide energy when the sun's not available, as well as carry the load at that given time. So if, for example, we had to run a ventilation fan on the greenhouse during the day, we have to make sure that we're generating enough energy to run the ventilation system, maybe even a water pump as well as charge the battery for the eventuality of the sun going down and having to run lights and whatever. So that's all part of the budgeting process. Generally, you calculate it for the worst case environment. So in terms of the number of hours available to generate electricity, the winter will be worst case for you guys, obviously. So you have fewer hours when the panels are fully illuminated. Of course, you want to avoid obstructions. Sometimes people will have trees in the way so that certain times of day, maybe a tree might be obscuring the sun a little bit. So you want to make sure that your solar panel has the broadest, clear view of the southern sky. Okay? You don't want to have anything that's going to affect that angular relationship between the sun and the panels. So when you figure out how much energy you need, when you calculate your energy budget, you can work backwards from there and figure out how many panels you need to have. So like if we had a budget, say that we decided we needed a kilowatt hour every 24 hours to handle all the loads that the system's going to need. So if we need a kilowatt hour of energy, and you understand that's a unit of energy as opposed to power, right? You always know the difference between power and energy. Is that evident to you? Energy is the integral, the mathematical integral of power. Power is energy per unit time, and energy is simply the integral of energy per unit time over, iterate over time. When you collect a certain amount of energy, that means you have the potential to do this much work, right? But the rate at which we collect that energy can be anything. And so if we find out that the solar panels are going to have, just for a number, we'll say they have 5 hours of proper illumination to get your specified output, then we know that within that 5-hour time, we have to be sure to collect and accumulate over that kilowatt hour of energy that's going to be required for the next 24 hours. And when you do that calculation, you have to take into account all the losses you have. Because like when the energy goes from the solar panel into the controller, there's actually a DC-DC voltage inverter inside the controller, and that has some losses. And then when you put the energy into the battery, the charging process has losses, so that the amount of energy you pump into the battery is not the amount of energy the battery actually has stored. There are resistive losses and chemical losses in transferring energy into the battery. Similarly, when you take the energy out of the battery, you have losses again, and that transition from out of the battery back out to the controller, and then from the controller to the light sources or whatever you're going to operate, you have losses in those loads as well. So in calculating the total amount of energy required, you have to take into account all those losses in one direction and the other, which actually bumps up your budget. You have to have more energy available to cover all the losses at each phase. So one of the things that will happen is, as we collect more information about the energy requirements of the farm, we're going to start looking at how efficient some of these things are. What kind of losses can we expect from different kinds of batteries? And again, you end up now with a trade-off. You can buy a really expensive battery that costs a lot of money, but it has very low loss. But you may not be able to replicate that all over the world because it's just too expensive. Nobody will buy it. So sometimes we have to do our calculation based on what's possible. So if we can only afford this quality of solar panel, maybe it's only 18% efficient, but it's inexpensive. So we can put more of them in the lower efficiency panels. Similarly, when you get a battery, you can get a battery that's really efficient, but they're thousands of dollars a piece, or you can get a battery that's less efficient and spend less money. So another ingredient in these calculations, besides the energy budget, is exactly how much money you have to spend on the system, which is going to modify the efficiencies for all the components. How many of you have heard of MPPT controllers? You know what that is? 2 people? Yeah. Excuse me. MPPT stands for a maximum power point tracking technology. I think I might have mentioned earlier that the solar panels themselves, they change impedance. Now, all of you at engineering should understand that to get the best energy transfer from one source to a load, you have to have the same impedance. You have to have impedance matching. Okay. And so since the solar panels change impedance throughout the day, depending on the kind of illumination they have and the temperature of the panels themselves, to get the best energy transfer into the load, you have to have the load change impedance to match the solar panel. And so the MPPT controller has a search algorithm inside it where it modifies the impedance of the controller, the apparent impedance, using a DC-DC inverter, so that it can find a point at which we get the maximum energy transfer from the solar panel. Okay. So you just need to be aware that the solar panel impedance does vary. Now, MPPT controllers cost a little bit more than some of the other types of solar panel controllers that are out there. It used to be that for some installations, MPPT controllers were almost too expensive. But today, they actually have some quite inexpensive ones available. I just bought one the other day from a company in China. I think I spent $35 or $40 for a 20 amp MPPT controller, and it works on 12 or 24 volts. Can anybody imagine why I might elect to build a 24 volt DC system instead of a 12 volt DC system? Oh, one step, yeah.
Conversion losses?
Well, conversion losses is a good idea, but the fact is that you can move more energy through a less expensive wire at higher voltage, right? So if I was trying to move 100 watts at 12 volts, I'd have to have, 8 amps at least, something like that, or 8, 9 amps. But if I was trying to move 100 watts with 24 volts, I only need 4 amps. So by using the higher voltage, I can reduce the size of my electrical conductors, which can save a lot of money. Copper wire can be expensive. And so the systems I've put in so far in Africa and Nicaragua, I designed them to be 24 volt DC systems to improve the efficiency of the transmission of the energy. Yes?
Do you only use copper or do you use aluminum?
Copper only.
Only copper? Is there any particular reason?
Well, it's availability. I mean, basically try to buy the material locally if possible. In fact, that's another thing about doing systems around the world. There's a huge advantage to buying as many components as you can locally, if only because now you know that those things are available locally. And so in future maintenance requirements, you're not going to be there to maintain it forever. And so you'd like to have mechanisms in place where the local people can keep it operating ad infinitum, So as much as possible, you want to buy batteries and everything locally. In Kenya, I was able to find some good battery suppliers that had AGM batteries and stuff. We're not going to talk a lot about battery technologies right now, but when we get into the design of the system, we'll discuss a little bit more about how the choice of batteries affects the cost and the efficiency of the whole system. Let's see what's next. So we've got the solar panels collecting some solar energy, generating some electricity. It's limited by the quantum efficiency of the solar panel, so maybe we don't need fusing there, special protection technologies. We might want to make it a 24 volt system, but I'm not guaranteeing that yet, but we're saying we want to consider the possibility of making it 24 volts versus 12. The kinds of loads we need. For example, I've put in refrigerators in some of these locations to support medical technologies. So if we put in these power systems to support a medical clinic that may be in a remote area, the refrigeration is very valuable. And so you can buy these little refrigerators now that are very efficient. I've been able to get a refrigerator to run on 24 volts and like 2 amps. And it's very easy to accomplish with a small solar panel array. And so we've been able to supply constant refrigeration in some remote places. It may only be a few cubic feet, maybe 2 cubic feet of storage space that's refrigerated, but it's enough to run the clinic's refrigerated requirements. And then, of course, we provide energy for lighting and to recharge things. So you recharge a cell phone or cell phones. In the systems that I designed so far, too, I generally always put in a radio, just for information's sake. You know, people live in remote areas often have no way to get knowledge of what's happening in their country or in their area. And so generally I try to install a radio receiver of some kind. They're very inexpensive these days. In fact, if you work in electronics, you can get a single chip that does a complete AM/FM radio in a single part, and they're very inexpensive. So adding a radio is it's almost a gimme. You know, it's not a big deal. And the amount of energy it draws is negligible. We're talking about milliamps, thousandths of an amp of current required for the radio operation. Any questions so far? Yeah.
If you're running DC on the load side, are you limited to some distances with your lights, etc., even at 24 volts? Your losses with lines and stuff?
It depends on how big the load is, of course. You know, if you had to move the energy a really far distance, then yes, you would definitely be limited. But again, you know, what we're trying to do is, you could call it distributed generation if you like, in terms of the power energy terminology. But we wanted to locate the power generation and the loads as close to one another as possible anyway. I found some water pumps, again from a Chinese supplier, very inexpensive, $15, $20, $30, and they can move up to 7 gallons per minute on 24 volts supply, and the current consumption was less than 2 amps. So you can move quite a bit of water around for just a small amount of energy.
So would you generally put in one central system, and then, or would you put in more than one system? Like
well,
if the loads were distributed?
one of the theories I had going into the project was the idea of an energy library, where if you go to a village, you could take one structure in the village and make it the center of industry for that village. And so for a very small amount of money you would install a small solar system on this one structure, have some lighting in there, perhaps a ceiling fan, maybe a refrigerator, whatever they need for that industry. So then now what's happened is you've taken that village of N number of families, maybe 10 families, and you've given them the opportunity to work after hours, early or late, at some industry. They could start weaving baskets or whatever it is they find to be a valuable industry. And we can provide technology to support that industry. If they need extra water, we can have a water pump in the design. If they need refrigeration, we can add that to the design. But we can take this one little structure and spend a relatively small amount of money energizing it, and then the village works with it cooperatively. And they also cooperatively support it. So when they need to replace the battery for storage, they pool their resources and generate a battery purchase. Yeah. So I find that, especially in places like Africa, the villages are very tight-knit. They've known each other for generations, and they're very good at working together, they're very cooperative.
I just wanted to add that for the foundation, one of the things that we wanted to offer was to teach people how to store their food in Canada, because that's a lost art. Grandparents used to do it effectively, but
without refrigeration. Yeah.
You're right,
Yeah.
but so that would come in handy as a way to demonstrate.
Right. Yeah. See, the idea I had for an energy library meant simply that those families who chose to would simply become part of the cooperative, and they would share their resources in maintaining it and using it however they wanted to. You know, they could form a small operation council, and maybe each family that's using the library would contribute a few dollars a year, or whatever it takes to keep everything operating, and so then they have access to that resource. And they could use the lighting anytime. They could come in and read or work on their basket weaving or whatever kind of industry they think is useful and valuable. So honestly, it doesn't take that much energy. Right now I'm working on another project in Florida where we're designing a project we call MOVE. And the idea is that we have a large truck, it's a big truck, and it carries thousands of small energy modules. You know, similar to the Serona project that they've done in Haiti. We're doing small energy modules, so we can move into the site of a hurricane disaster. And this truck carries in it the capacity to recharge these energy modules, as well as to bring in satellite internet access and information from television and so on. And so now, people in an energy or in a disaster zone could come over to our trailer, and they could use their Wi-Fi on their phones or whatever, and they could send emails to their friends and family around the world. They could check on availability, they can even order materials they need to rebuild their home. And then we're going to give out these little modules. We're not even going to charge for them. We'll give out these energy modules to the people that have suffered the losses in that area. And with that energy module, they can provide a little bit of lighting for their home, recharge their cell phones, and maybe recharge a tablet or something. And then they can bring it back to the van to swap it for another one that's recharged already. We're going to carry a few thousand of those aboard this truck. That's an IEEE project that we're doing in the southeast U.S. And so I'm doing a lot of the engineering for that right now, designing all those systems.
With any of your critical systems, like if it's a hospital or whatever, where you got refrigeration, do you have some type of backup system to that? Do you have a small generator of any type in the system?
No, it's expensive.
It's all
you basically have to have enough storage, the batteries, to handle whatever length of time you would expect for an outage. So if you may have an outage for 4 or 5 days or whatever, because of constant rain or something, the solar panels will still generate, but at a much lower rate.
Yeah.
And so
it's totally on solar and batteries.
Yes.
Okay.
And that's all part of the calculation. You figure out, the worst case we'll have to work at 10% energy for 5 days. And so in that instance, we have to have enough storage to handle that. Only 10% income from the sun.
Does your system regulate that at all? Like, does it say,
It
okay,
does.
this is critical?
The system I designed that we put in Kenya actually has energy priorities.
Okay.
And so as you plug in the different loads, they've been assigned priorities. And so as it detects that the battery charge is getting lower, it'll automatically disconnect lower priority loads so that people can inadvertently waste all their energy on things that are less important. For example, one of the loads, if they have a water pump load, is a really big one, and it can suck the battery down fast. What you might do is put in technology that says, well, the water pump can only run when the sun's out. And then when the water pump's running, you store it in some kind of elevated tank, and then you have gravity feed otherwise at times. So just don't allow the water pump to run except when the sun's shining brightly, and then you don't have to worry about it sucking your battery down quickly, things like that. But the priority loads would be things like maybe lighting. You would want to have light available whenever it's required. Refrigeration might be a priority load. And so the intelligence inside of the load management system I designed is doing all those calculations. But that's an important thing too, is to understand the priorities and what is the critical load. I think it may not be intuitively obvious all the time what's critical to this population. These people, they have certain needs and ideas as to how they can use energy that may be different from what you've always imagined. And so it's really important to be in close communication with the end user and understand what their universe looks like and what they see as being useful. When we go to the farm, I was hoping we'd be able to talk to the end users there, and so we can get, all of you can get a first-hand understanding of what they see as the challenges in terms of energy needs at the farm. Let's see if there's anything else we should talk to before we go to the farm. When we get to the farm, we're going to want to do a few things. One of them is to get just a site map. We want to lay out the buildings and sort of the large trees that are in the area, just sort of drawn on a piece of paper. And Joan has some nice big paper for us to use. I brought along a compass. I think Glenn has a big long measuring tape. So we'll sort of do this a very simple, crude survey of the space to see exactly where everything is. For several reasons, we want to look at likely sites for the solar array, wherever that might go. We might need to have more than one solar array. And if we have to move energy from one place to another, how far is it going to be? And so what kinds of carrying capacity does the wire require to move the energy that far? The greenhouse building itself is 75 feet long, right? It's
72.
72 feet long and 17 feet wide, is it? So that's some distance. Yeah.
Yes. It's a hoop house. Does that make a difference?
No, not
Okay.
really.
I was thinking, but one of the things that in our plans is to have at least 3 in the next couple of years. So expand it.
So you'll see it when you go to the farm, but they have this long semi-cylindrical thing. Basically it's a half cylinder, 72 feet long, 17 feet wide. And that's where they grow all the plants. One of the challenges in there is going to be managing the temperature. We don't want it to get so hot that it wilts everything, and makes it impossible for humans to get inside. Similarly, if we can help it in the wintertime, that would be really useful as well. Have you had much luck farming in the winter in that thing?
We usually end at the end of October. And we plant a few little things that are what they consider winter, can take some winter, like lettuce and stuff like that, kale. But typically at the end of October, and we don't start planting until February again.
You know, one way you could collect heat, in fact, I have an indoor pool at my house in Florida, and I swim all year round because I heat the water from the sun. One of the things we might consider to expand your growing season is we could collect heat in some fluid, maybe water, and run it through the inside, you know, so we could have solar collectors on the outside collecting heat as much as they can, and then circulating that through the inside of the greenhouse with some type of heat exchanging device. Yeah.
What type of thermal do you use for your pool?
What kind of thermal?
What kind of solar panel?
Oh, they're capillary. No, they're
Evacuate
capillary
tubes.
pools. They're panels. They're just big black plastic panels with little capillary lines in them. They're black, and so they collect heat energy and they heat the water up inside. And I have a pump that moves that water into the pool.
You use a pool pump for that?
Yes, I use regular pool pump for that.
Yeah.
Yeah, actually, we've been able to run our
works in
pool.
Canada, too.
My wife likes the pool so hot. I mean, it's like a sauna in that room. I like it a lot cooler. But yeah, you can get a remarkable amount of heat energy from the sun as well. And so that might be a separate array. Maybe we would have an array of capillary thermal panels that provide some more heating energy to expand your growing season. And then we might also have the photovoltaic panels as well to do this.
Have you had any experience with evacuated tubes? For
What kind of tubes?
Evacuated, vacuum?
Oh,
Where
no.
the rods
I haven't
are
ever
vacuum.
tried that. I haven't. No.
Yeah, I've just used the same thing as you've got with the small tubes, black plastic, but it picks up ambient temperature. So in Canada, October,
You don't get much energy from it.
No, but they have evacuated tubes where they're basically copper tubes inside of evacuated glass tube.
Oh, that would be much better, yeah.
And it runs into a header.
Yeah.
And I know this, I saw on the web, there's some guy in Edmonton's heating his shop floor through radiant heat with this at -30.
Well, you can do the same thing. If you put some kind of insulating plastic enclosure around the black capillary, you can improve the direct ambient impedance, you know. There's a thing called thermal resistance, which is the amount of energy it takes to move heat from one place to another. And so if we can increase the thermal resistance between the air and the heat exchanger, then that'll improve the efficiency as well. Yeah. That's something we'll talk about when we talk about the way we mount the solar panels and so on, is the thermal impedance, how much heat gets moved around. When I do electronic designs, and I design electronics for all kinds of things, I've done stuff for the space program and fighter aircraft and high altitude flight. In general, when you design things electrical, or actually any engineering at all for that matter, managing the thermal problem is the biggest problem. When I design things, people pay me a lot of money because I can make sure that they last a long time and they meet expectations, because I'll make sure by virtue of my thermal calculations that I don't overstress any of the components. The biggest life accelerant to any electronic component is heat. So if you learn how to manage heat properly, you can make stuff last a lot longer, both structurally and electronically. So it's really important to understand how to manage heat. That's one thing they don't teach much. I lecture many universities around the world, and in general, when they teach electrical engineering courses, they don't spend nearly enough time teaching about heat management, which is so critical to successful designs. Okay, what else should we talk about for the farm? We're going to do a little site survey, measure some distances. Does anybody know what magnetic deviation is? Have you heard that before? You know what it is? Anybody? You've been in the service, maybe? No? You've been in the military? No? Okay, it turns out, so those of you that don't know, the magnetic North Pole of the Earth is actually in Canada. It's not near the North Pole for real. And so that causes a deviation. So when you use a compass to measure the direction to the North Pole, You're actually pointing to a place in northern Canada, you're not pointing to the actual North Pole. In this part of Canada, your deviation is about 11 degrees. And so when you use your compass is going to point 11 degrees west of where north really is. And so when we go about aligning our panels, you have to understand that for this location where we are right now, and it varies very quickly. If we were to move 100 miles in either direction, it'd be a different angle. And so it's important that you understand that where we are here in Oshawa, it's about 11 degrees difference. And so when you're going to find out where true south is, you can use the compass, but then you have to compensate for the difference in the fact that the North Pole is there and your magnetic pole is here. Let's see what else. I think that's enough information to prepare us for the trip to the farm. Again, we'll have a short interview basically to find out about what the end users think they need, do some measuring.
That's Glenn and I.
Sorry?
That's Glenn and I.
Oh, that's Glenn and you, that's right.
There might be other people there.
Mm-hmm. And then do the site survey and make a little plot so we can see the layout. And I don't really have to worry about elevations. This is a relatively flat area, I suppose.
And open.
It's open. That's good. Any other questions? Well, next is the field experiment, where we go out and collect some data and do some drawings on the nice paper that John brought. Well, thanks for your attention. I hope you learned a few things this morning. And if you have any questions, feel free to ask me.
So does everyone know how to get to the location?
I need to use the restroom myself real quick.
Okay.
I got room. I got room, that's right.
Okay, so it's
But I don't know where I'm going.
Hi, sir. Hey. So we'll figure out who needs a right in a second. I'll give you the directions. It's north on Simcoe to Winchester, left, and it's number 200. Big
So
sign.
Winchester, 200. Is that north or south side?